Okay, now let's focus on the general form of low pass filter and high pass filter. So I want to show you how the general form for the transfer function of these two type of circuit looks like, how they look like, and then later we're going to focus on different circuits, how we can design a low pass or high pass filter, and how we can determine which type of filter we are looking at. So here I'm going to show you low pass filter general form, and on the other side I'm going to show you high pass filter. Okay, the general form for the transfer function of low pass filter looks like this. We have a gain of K, and then we have omega C, which is our cutoff frequency, over S plus omega C. And for high pass filter, again we have the gain, but this time in numerator we have S over S plus cutoff frequency. Let's see why the first transfer function can be considered as the general form of low pass filter, and then we are going to focus on high pass filter. In order to figure out if you are looking at a high pass filter or low pass filter, what you have to do is that you have to evaluate your transfer function at low and high frequency. So you have to look for the values where omega is very small and when omega is very large. So let's assume that omega is very small. So I'm focusing on low frequencies. In low frequencies, when omega is very, very small, then this term can be neglected. We can throw away this term because this is a very small number, and then what we have left is basically the gain, because then omega C and omega C cancel out. So the filter has a gain of K when we are focusing on very low frequencies. Now, if we go to high frequency, so if we focus on higher frequency, what happens is that this time, comparing S and omega C is much smaller than S because we are thinking about S as being infinity. So we can neglect omega C here. So what we are going to have is K multiplied by omega C over infinity. K multiplied by omega C is a constant number. A constant number over infinity is close to zero, is going to be close to zero. So if we focus on high frequency, then the gain of this filter is about zero. So if I plot the frequency response, the magnitude of your transfer function, h of j omega, at low frequencies are close to K, and at high frequencies it's going to be close to zero. So it's going to be something like this. And this is similar to an ideal for K equal to 1. This is similar to an ideal low pass filter. So we consider something like this to be a low pass filter. Now, let's go to high pass filter and see why we consider this transfer function to be the general form of a high pass filter. So again, what we have to do is that we have to focus on low frequencies and high frequencies. In low frequency, again, I have something close to, I have to consider my S to be very close to zero. So what I have is basically 0 over 0 plus a number. So 0 over a constant, which is omega C, and that's close to 0. And if I'm focusing on higher frequency, then this time, considering this one as infinity and this one as infinity, omega C can be neglected here. So I have k multiplied by infinity over infinity. These two cancel out each other, and what I'm going to have left is k. So let's look at its frequency response plot this time. This time I'm having 0 magnitude for lower frequency and a magnitude equal to k for higher frequency. So this time I have a frequency response plot like this, and again this can be considered as a high pass filter because it has similar behavior to a high pass filter. Obviously it doesn't have the sharp transition, and that's normal because we are trying to you're going to see that we will make this filter with very simple component, with only one resistor and inductor, or one resistor and capacitor. And basically when we don't have that sharp transition between the pass band and stop band, we call this one as a first order low pass or high pass filter. So what you can see here, this one is basically the transfer function, the general form of transfer function for a first order low pass filter. And what you can see here is the general form for the transfer function of a first order high pass filter. So don't forget that what we are discussing here is just a first order low pass or high pass filter, which basically means that's the simplest form that you can have for a low pass or high pass filter. Okay, now I want to show you two different circuits that behave like a low pass or high pass filter, depends on which parameter we are selecting to be our output parameter. So in order to have a simple first order low pass or high pass filter, what we need is a simple RL or RC circuit. Remember that if you use an RLC circuit, then you ended up having a band pass filter or band reject filter. But with RL or RC, you can have high pass filter or low pass filter. So because in this lecture my focus is on low pass filter and high pass filter, I need to have RL or RC circuit. So let's look at these two circuits, and then we're going to discuss their behavior together. So I'm assuming that I have an RC circuit. Here I have R, and the impedance of the capacitor is 1 over CS. Then VI is the voltage of my input source, and let's assume that VO is the voltage of my output. Another circuit I want you to look at is an RL circuit. So this time I'm gonna have an inductor in series with a resistor. The impedance of inductor is LS, and here I have R. Again, the voltage of my input is VI, and the output voltage is going to be the voltage of resistor, or VO. In the first circuit, which is an RC circuit, I want to look at the transfer function that describes my output as VO and my input as VI. In this circuit, you can see that this voltage of VI is being divided between the resistor and capacitor. So if I want to describe my VO of S, that would be 1 over CS divided by 1 over CS plus R multiplied by my input voltage. So using a voltage divider, so what I have here basically is a voltage divider. I can use this voltage divider equation and describe my transfer function, which is VO over VI. So VO over VI is going to be this term, and I'm going to multiply everything by S over R in both numerator and denominator. And what I'm going to have is 1 over RC in numerator and s plus 1 over RC in denominator. So what I did is that I used this voltage divider equation, and this 1 over CS over 1 over CS plus R is basically my transfer function, which describes the relationship between the output and my input. However, in order to make it looks like one of those two general form of filter transfer function, I'm also multiplying everything by both numerator and denominator by S over R. So if I multiply my numerator and denominator by S over R, this is what I'm gonna get. And you can see here that it does have the format for a low pass filter. If I show you the format of the low pass filter, that's here. This is a low pass filter. So in a low pass filter, in denominator, I have S plus omega C. So let's go back to this circuit. So according to this fact, this is my omega C, and in numerator, I'm supposed to have a constant value, which is the result of my gain multiplied by my cutoff frequency. So what I have in numerator is a constant gain. Because I have a constant gain in numerator, I'm assuming that this is the transfer function of a low pass filter. So let me remind you, if you have a first order transfer function, so in denominator for both high pass and low pass, you're going to see S plus a number, which is your cutoff frequency. Now, the difference that describe if this is a low pass or a high pass is your numerator. If in your numerator you have a constant number, then that's a low pass filter. If you have S, something multiplied by S, then that's a high pass filter. So what I have here is basically a low pass filter. In which its cutoff frequency is equal to 1 over RC, and as you can see, the gain is equal to 1, because here in numerator I have K omega C, and because that's exactly equal to omega C here, I can conclude that K is equal to 1. So this is my conclusion for this circuit. So this circuit, if I focus on the voltage of capacitor, then it will behave like a low pass filter with a cutoff frequency equal to 1 over RC and a gain equal to 1. Now, I want to see what happens if I focus on the same circuit, but this time, instead of looking at the voltage of capacitor, what happens if I look at the voltage of my resistor? So I'm going to choose another color. So here this time I want to see if my output voltage is the voltage of resistor, what will happen. So if I focus on this one, this voltage, I'm going to write everything on a new slide. So if I focus on what I have here on the voltage of the resistor, then I can use the voltage divider, but this time in numerator, instead of 1 over CS, I have to use R. So my VO is going to be R over R plus 1 over CS multiplied by VI. So my transfer function will be R over R plus 1 over CS. Now I can see that this is a first order transfer function, but it's not yet in the form of my general transfer function. What I need in denominator is S plus something, so I need to create this S. So what I'm going to do is that I will multiply everything by S over R again. So if I multiply everything by S over R, this term will have S and R will cancel out, so then I'm going to have S plus something. So let's do the calculate, do the arrangement. So if I do the multiplication, what I'm going to have in numerator is going to be S. And in denominator, the first term will be S, the second term, S cancel out S, and I'm going to have RC. So now you can see what I have here is basically the transfer function of a high-pass filter. Why? Because we discussed that whenever you have a constant in numerator, that means that you're looking at a first-order low-pass filter. If you have S in numerator, which we have it here, then it means that we are looking at the transfer function of a first-order high-pass filter. So I can say that what I have here is a high-pass filter in which omega c is equal to 1 over RC and k, which is the gain of S in numerator, is equal to 1. So my main conclusion here is that with an RC circuit, you can create either a low-pass filter or a high-pass filter. It depends which component you are looking at. So if you're looking at the voltage of capacitor or if you're looking at the voltage of your resistor. In both cases, for both low pass and high pass filter, the cutoff frequency is fixed. The cutoff frequency is 1 over RC. It doesn't really matter. So as soon as you decide to work with an RC circuit, your first order low pass or high pass filter's cutoff frequency is going to be 1 over RC, but depends on if you're looking at the voltage of capacitor or the voltage of resistor, you're going to have low pass or high pass filter. So if you look at the voltage of your resistor, then you're going to have a high pass filter in an RC circuit. If you look at the voltage of capacitor, then you're going to have a low pass filter. So this is an important conclusion here. So if I ask you to make a low pass or high pass filter with RC, you should be able to do that. And the only thing you should be careful is which voltage you need to look at. Okay, now let's go to the second circuit, which is an RL circuit. So here I want to show you what happens if you have an RL circuit and what type of filter, first order filter, you can make with this particular combination of element. So if you have an RL circuit, first let's focus on the voltage of its resistor. So if I want to describe VO, again, I'm going to use a voltage divider and I'm going to have R over LS plus R multiplied by VI, which is my input voltage. Now again, I want to get rid of the coefficient of S here, so I have to divide everything by L, and my H of S, which is VO over VI, is going to be this one, but I'm gonna multiply everything by 1 over L. So I'm gonna have R over L divided by S plus R over L. So you can see here that what we are having is a low pass filter. Why? Because I have a constant in numerator. And the cutoff frequency from here, I can say my cutoff frequency is equal to R over L, and the gain is equal to 1, because in numerator I have k omega c, and since the numerator and cutoff frequency, they are exactly the same, then it means that my gain is equal to 1. Now let's see what happens if I focus on the voltage of inductor instead of capacitor. If I focus on the voltage of inductor instead of capacitor, then what I'm going to have is, I'm going to continue on the next page. So what I'm going to have is going to be VO over VI as LS divided by LS plus R. So this time, because I'm focusing on this voltage, then in voltage divider, I'm going to have LS over the total impedance. So I need to simplify this. I have to get rid of the coefficient of S to see what is my cutoff frequency. So I'm going to multiply everything by 1 over L. And my transfer function simplifies to S over S plus R over L. Now, if I look at this transfer function, this time I can see that I have S in numerator. So because I have my Laplace variable in numerator, I can say that this is a high-pass filter with a cutoff frequency equal to R over L. And the gain, which is the coefficient of S in numerator, is equal to 1. So this is my conclusion. Now I'm going to make a table and I'm going to show you all conclusions. So let's assume that we can make our circuit by capacitor or inductor. So we can have RC or RL circuit. If I'm having RC circuit, then I might focus on the voltage of capacitor or the voltage of resistor. And in our RL circuit, again, I will focus on the voltage of inductor or the voltage of resistor. Now the question is that what type of filter I'm going to have if I'm looking at, for example, the voltage of capacitor in an RC circuit, or the voltage of resistor in an RC circuit or in RL circuit. So if I'm having an RC circuit and I'm focusing on the voltage of capacitor, then I'm going to have, so in this scenario, I'm going to have a low pass filter. And if I look at the voltage of resistor, I'm going to have a high pass filter. So this is my answer basically. And if I'm having an RL circuit, by focusing on the voltage of resistor, I'm going to end up having a low pass filter. And if I focus on the voltage of inductor, I'm going to get a high pass filter. So if I ask you, so this is an important table because it helps you to know which voltage you need to focus on. So in the design, in the design process, if I ask you, for example, I need to have an low pass filter with an RC circuit. So with an RC circuit, if I need to have a low pass filter, then I have to focus on the voltage of capacitor. So you can make low pass filter with both RC and RL, and same thing for the high pass filter. The only tricky part is which voltage you have to look as your output voltage. So if you focus on the voltage of resistor in an RC circuit or the voltage of inductor in an RL circuit, you ended up having a high pass filter. And if you focus on the voltage of capacitor in an RC circuit and the voltage of inductor in an RL circuit, you ended up having a low pass filter. So this is something you should know, and this table can be helpful when you're designing your low pass or high pass filters. Okay, now let's do a very quick design example here. So this is an example. Let's assume that we want to design an RL low pass filter with a cutoff frequency equal to 10 kilohertz, which has a cutoff frequency equal to 10 kilohertz. Okay, so now in order to design an RL low pass filter, let's see what do we need. if we are focusing on our L circuit and we are looking for a low pass filter, then it means that we need the voltage of our resistor to be the output voltage. So I'm gonna draw my circuit in this form. This is my VI, and I need to have the voltage of resistor to be the output voltage in an RL circuit to provide a low pass filter. Now the next question is that what should be the values of R and L in this circuit to have a cutoff frequency equal to 10 kilohertz. So in order to find the cutoff frequency, I know that the cutoff frequency in our C circuit is equal to 1 over RC, and in our L circuit, it doesn't matter if it's low pass or high pass, it's going to be equal to R over L. So what I know here is that R over L, which is my cutoff frequency, is equal to 2 pi multiplied by 10k. So as long as the ratio of R over L is equal to 2 pi multiplied by 10k, then this circuit will have a cutoff frequency equal to 10 kilohertz, and it will act like a low pass filter because I'm focusing on the voltage of resistor in RL circuit. So let's assume that I have a 5 kilo ohm resistor in my lab, and I'm going to use that as my resistor value. So I'm going to choose R to be 5k. So if I choose my resistor to be 5k, then I'm going to have my inductor value equal to 5k over 20k pi, and that's going to be equal to 0.08 Henry. So it tells me that my inductor value should be 0.08, my resistor value is 5k, and using these values for inductor and resistor and focusing on the voltage of RL circuit, I'm going to have what it was asked for.